So my name is Cristina Nizzarotaro. I'm a professor at Northeastern University, and I'll be chairing this session. We have 4 very interesting talks. And as before, the talk is going to be 16 minutes, and please hold your questions till the end and try to stay within time. So with that, let's start with the first talk. It's going to be given by Sundar Muthu from UCL, and I'll let him introduce his paper. Whatever you want to ask. Yeah.
Can everyone hear me? Okay, great. Cool. Good afternoon. I'm Sundar, and today I'll be presenting our work, FPFED, Privacy-Preserving Federated Detection of Browser Fingerprinting. This is joint work with Igor, who is in the audience, and Emiliano, my advisor, who's also in the audience. First, I'll be going through what browser fingerprinting is. As you may already know, users are often tracked online using many different tagging technologies, the most famous of which is third-party cookies. However, in recent times, browsers have also begun blocking or restricting these third-party cookies. In response to this, online trackers have moved to other kinds of tracking technologies, namely browser fingerprinting. In browser fingerprinting, a set of information is collected from a user's device that makes it uniquely identifiable. This can be hardware-based information, such as the number of CPU cores on your device, but also can be software-based, such as the version of a particular software that's installed. Browser fingerprinting is typically deployed through a JavaScript program that runs in the browser and is commonly seen as an invasive tracking technique. This is because browser fingerprinting is stateless. Compared to cookies, no information is stored in the browser. This makes it hard to prevent and less transparent. There are many different kinds of browser fingerprinting techniques. One example is canvas fingerprinting, which you can see here. In this case, the script exploits the differences in the way that different devices render the same image. And this can be used to then build a fingerprint or a hash of a single user. There are also other kinds of browser fingerprinting techniques, such as canvas font, and also audio, which looks at the number of different fonts that are installed on the device, and also how audio is processed by the device. One of the main challenges in browser fingerprinting is detecting it in the wild. Prior work has focused on manually curating block lists and heuristics. However, these are hard to maintain and are often narrowly defined, thus missing many fingerprinting scripts in practice. More recent work has also moved to using centralized machine learning techniques based on automated web crawls. However, since the crawls are automated, they cannot replicate real-world human interactions and are often blocked by bot detectors and also captchas. Furthermore, these centralized machine learning techniques often use a large number of features in the range of 2,000. Overall, prior work on browser fingerprinting detection might miss many fingerprinting scripts in practice. Now, one way to solve this problem of missed fingerprinting scripts is to just gather real-world observations from users as they browse the websites. However, as the data collected might contain sensitive information, this might affect users' privacy in practice. This is where differentially private federated learning comes in. DPFL is an approach of learning from the private information of many participants without revealing the underlying raw data to a centralized server. One of the famous algorithms for doing so is dpFedAverage. In dpFedAverage, each user first builds a local data set and trains their own local model on that data set that they have. Next, the updates to the local model is then propagated to the server. The crucial thing to notice here is that the raw data remains on the device, and only the updates are sent to the server. The server then aggregates all of these local model updates, and in our case, we also add statistical noise to preserve DP. In the end, the updated model is then shared with all of the users, and this is repeated in rounds until the global model converges. One of the main challenges, there are many challenges to applying DPFL to browser fingerprinting. Firstly, it's not trivial to federate existing classifiers efficiently into the federated setting. Furthermore, given intensive feature extraction and complex algorithms that go into the processing of these features, this might affect browser performance when users are using the browser. Lastly, as we add statistical noise, DP might introduce a privacy utility trade-off that has to be tuned. This brings us to our work, FPFET. FPFET is a distributed system for detecting browser fingerprinting in the wild. It solves the aforementioned challenges by first requiring a minimal number of features and also achieves good accuracy with minimal false positives, even given formal privacy guarantees, therefore balancing the privacy utility trade-off. Overall, our system enables us to use and learn from real-world browsing patterns while preserving the privacy of the users. Now I'll present our system. In our system, first, each user will install an instrumented browser which collects the scripts that are loaded by each website that they visit. Next, we extract a set of features from these scripts. Firstly, we collect the number of times each monitored API is called. This is because, for example, if the measure text API is called many, many times by a script, this is often indicative of fingerprinting behavior. On top of this, we also collect a set of custom features which are post-processed from the arguments and return values of the API calls. In total, we collect a total of 1,500 features. Next, we assign ground truth to each of the collected scripts using a ground truth heuristic that was introduced by Igor et al. In prior work. This ground truth heuristic focuses on 4 main types of fingerprinting: canvas that I've already gone through, canvas font, WebRTC, and audio context. Lastly, all of the features that are collected by the users are then pre-processed using feature normalization techniques. This is known to improve the convergence of a model in the centralized setting, but in our work, we federate it and add statistical noise so that it satisfies DP as well. In the second step, the participants then run the DP Fed average algorithm, which was already introduced before. Now that the system is in place, I'll be going through the experimental setup that we used to test our system's effectiveness. Although ideally we would want to collect real-world browsing sessions and test the FPFET system on top of these real-world browsing sessions, for the purposes of this work, we wanted to test the viability of such a system in the first place. Therefore, we collect an automated crawl of 20,000 popular websites. Based on these 20,000 websites, we collect about 181,000 unique scripts, out of which 752 were found to be fingerprinting. Next, we simulate the participants on top of this data set by assuming that each participant samples from the top 100 domains according to the popularity. Then, the scripts that belong to these domains were assigned to each of the participants. Although our system is quite modular and can be instantiated with any modern ML model, we found that a simple logistic regression model was enough to give sufficient model effectiveness. Furthermore, as the output of the model can be thresholded, and this threshold be adjusted at many different values to achieve the necessary precision recall, we report the area under the precision recall curve, as this summarizes the model performance across a variety of thresholds. Lastly, one of the main things that we studied was to reduce the number of features required for the detection of browser fingerprinting. This is because collecting a large number of features can be computationally intensive, but also raise privacy concerns. Therefore, we also test with smaller feature sets, such as the FP Inspector and JShelter feature sets, which were presented in prior work, and also look at the APIs that are already being natively tracked by Google Chrome. Now, I'll be going through the results of the model's effectiveness in practice. Firstly, we study the impact of the privacy parameter, which basically looks at how much privacy is given to each participant, along with the total number of participants indicated by W. What we find is that even though only a few participants are sampled in each round, the total number of participants is important to the model performance. As you can see, at high privacy levels of an epsilon equals to 1, when the number of participants is 10,000, the model performance can be very low. However, when you increase the number of participants to 1 million, the model performance dramatically improves. And this shows that having a large number of participants can often be beneficial, even if not all of them are participating in each round. Next, we also look at the impact that the feature set and the number of features has on model performance. We find that while having a small number of features, such as the JShelter feature set, which only contains 40% of the features, can still produce good model performance. When you have too little, which is indicated by the high entropy feature set, the model can be ineffective even when we don't add any DP noise. This naturally brings us to ask the question of what would be a minimal feature set to work with. What is the smallest number of features that are necessary for the model to give good results? This can further be broken down into how many API call counts that are necessary and how many custom features. We go about studying this by looking at the feature importance score, by assigning a feature importance score to each feature and sorting these features according to the score. Then we incrementally add these features back to the high entropy feature set. What we find is that, firstly, no amount of API call counts is enough to reliably detect browser fingerprinting in practice. This can be seen here, as even at 684 features, the model still does not perform well. This brings us to the point that we definitely need some custom features to reliably detect browser fingerprinting. We find that when we add custom features, past a certain point, the model performance momentarily drops, especially at high privacy levels. And this is because as you increase the number of features, the amount of noise that's present in the system also increases. Therefore, we find that the sweet spot is around 40 additional features to the high entropy feature set, which is optimal for good model performance. Lastly, as we were the first work to look at differentially private federated preprocessing, we also look at the impact that this has on the model performance. And what we find is that our DP-Fed norm algorithm is actually able to improve the model performance by up to 20%. And this shows that in DPFL settings, it might be useful to assign a small amount of the privacy budget to the preprocessing of the features, as it improves the model performance as well. In our paper, we also include further experiments on non-IID distributions and show that FPFET is robust to this as well. Although I've already gone through some of the good points about our system, there are certain limitations that has to be addressed. Firstly, in our work, we only focused on a simulated setting as we wanted to test the viability of the system. In future work, we would also want to look at real-world browsing sessions and how FPFET is able to perform in that setting. Next, especially at high levels of privacy, we notice a large performance drop, which needs to be improved if we want to achieve this in practice as well. There are also a number of real-world considerations, such as how we handle devices that may drop and join the system arbitrarily. And lastly, the ground truth heuristics that we used was based on the 4 main types of fingerprinting that are currently present. However, when newer JavaScript APIs are introduced, this can change, and we will need to update the heuristic as well. In summary, I've introduced our system, FPFET, which applies DPFL to solve the problem of detecting browser fingerprinting. Our work enables us to learn on real-world browsing instead of automated crawls. It's also an efficient system as it requires a minimal feature set compared to prior work. Lastly, it is able to achieve an acceptable level of utility even with strong privacy guarantees. Thank you.
So I'm going to ask an obvious question. What about attacks against federated learning? What about clients that maybe want to do poisoning or backdoor poisoning? Have you looked at that or considered?
So we have not explicitly looked at that in this work, but there have been prior work that has looked at how DP helps with the robustness of the federated system as well. And if we were to deploy this, we would also test those aspects. But in this work, we didn't look at it.
Alexandra Dmitrienko, University of Würzburg, Germany. I would like to get some little more details on the data set. You said you had 700-something samples, which are fingerprinting scripts. How did you identify them as fingerprinting?
Using the ground truth heuristic. So basically, it's the same ground truth heuristic that the system uses. It basically looks at the 4 main types of fingerprinting. Sorry, let me just go back to the... Okay, it should be, yes. Okay, got it. So basically, these 4 types of fingerprinting, there's been established prior work on how to identify them very precisely in practice, and we use that to then label the scripts as well.
So basically, in this work, you just tried to make it more privacy-preserving, so to say, right?
Yeah.
Okay, I see.
He was first, and then...
Hi, my question was kind of similar to the last one. It's just, I see this as a simulated setting. In a realistic setting with federated learning, how would you do the local labeling of this is a fingerprinting attack? And so in your training, you would know that this to train this as fingerprinting to build the model.
Yeah, so it will still need to depend on some kind of heuristic in order to label it. And that also gives us a limitation on like what's the heuristic that we are going to use now. But yeah, that is the same answer. I hope that answers your question. Thank you.
Yes, my question is about the aggregator in the Fed average.
Mm-hmm.
So if I understand correctly, you apply the DP noise at the aggregator,
Mm-hmm.
which means that the aggregator can de-anonymize or fingerprint users based on the updates. Do you plan to mitigate that?
Sorry, I didn't catch the last part. The aggregator.
The aggregator can try to
Okay, yes, okay, got it.
de-anonymize
Yeah.
or...
Yeah. So in this setting, it is, I mean, I didn't go through this, but we are looking at the central DP setting where the participants depend on, or rather trust on the aggregator. And, but we did not look into the local DP setting where the participants don't trust the aggregator. The main reason is because in local DP, usually the model performance gets too adversely affected. But yeah, no, we didn't look at it. Thank you.
Hello, Yi Chankaya from UCSB. So when you generated the participant in your simulation, like, did you experiment with different distributions?
Yes. So, sorry, is that the question or?
Yeah, like
Okay.
for example, like vastly different behaviors between different participants.
Yes. Okay, so this is something that we looked at and it's in the paper, and we can take this offline later if you want to as well. But mainly, we looked at non-IAD distributions where each user only is able to. So we varied it as well, but the extreme setting is each user only each user only sees a specific type of fingerprinting, and even in these settings, the system was robust to detect browser fingerprinting. Yeah, thank you.
Let's thank the speaker. Thank you.
Thank you.